Virtual reality is a technology already established in many different markets and platforms around the world. With the increasing popularity of virtual reality, many video games and virtual experiences with high visual quality have been developed recently. The use of mobile phones emerges as a low-cost alternative for virtual reality. However, the hardware constraints of these devices restrict the displayable visual complexity. Considering the limitations of hardware and graphic processing of mobile devices, the supported scenes are usually graphically very simple, with the rendering of complex 3D scenes being a challenging problem. One popular technique used to solve this problem is image-based rendering. This technique relies on a set of two-dimensional images of a scene to simulate and render some novel views of this scene. Seltzer and contributors introduced a novel technique to display high visual quality 3D scenes in low-cost virtual reality devices. More specifically, they presented a technique to simulate a 3D environment by using a spherical panorama 3D texture matrix and dynamic image warping. That technique allows a fully 3D VR navigation and performs well in low-cost VR devices. However, that technique is not suitable for real-world environments, where the support of collisions and irregular surfaces represents a challenge. In this work, we present a technique suitable for real-world images that handles collision and irregular surfaces for an image-based rendering technique in low-cost virtual reality. The original technique simply iterates through the virtual scene and captures panoramic images with a predefined distance between images. However, this does not reflect what happens in a real-world environment, where images cannot be captured in the positions where the physical camera collides with objects. The image capture process should follow the same rules for virtual environments. In order to detect collisions, all the virtual objects and the virtual camera should have a collision volume, which is called a collision component in Unity 3D. Thus, while the virtual camera iterates along the desired volume, if there is a collision with any other object, the corresponding image is not stored. When the user is navigating to a position when there is no corresponding image, the system knows that there is an obstacle in that position. This is handled by the locomotion system, stopping the user from moving forward. Most virtual or real-world environments have an irregular or uneven surface to navigate on. However, storing the topography of the scene could be very complex and impractical for an image-based rendering technique. To solve this issue, instead of capturing images from different heights, we now only capture the images that correspond to a defined eye level above the surface. Hence, the simulation will treat these images as a flat surface, reducing the complexity of navigation techniques in low-cost VR. Users can use any navigation technique for low-cost VR to walk on a flat surface, but in this example, they will experience going down the hill. Thus, even though the height is the same for every image, the technique creates the illusion that the terrain is uneven. The distance between images is an important concept that affects the performance of the technique. It is necessary to find a distance between images small enough to create a smooth and realistic transition between images, but also big enough for the whole system to be usable and practical. We also conducted a user study in which 18 participants navigated through 2 virtual environments using our technique with 7 different distances between images. Results suggest that for those environments in which there are objects close to the camera view, a smaller distance between images should be used in order to avoid noticeable jumps between images and the sensation of going through objects. We suggest to use a value not bigger than 60 centimeters for small environments or when objects are really close to the camera view. On the other hand, for open environments in which there are no objects near the camera view, the study suggests that a distance between images of 2 meters, 4 meters, or even bigger can be used. This technique can also work with real-world environments by capturing 360-degree panoramic spherical pictures separated by a defined distance between images, thus allowing a virtual navigation through a totally realistic environment. The results are very promising since, for a real environment, the number of required captured images would be considerably reduced. One of the main benefits of our technique is that it does not depend on the visual quality or complexity of the virtual environment. The results prove the benefits of our technique for both virtual and real-world environments.